Hello everyone. This is part 2 lecture of the same topic non-rigid rotor and continuation of part 1, and you can remember that I have promised that I will show you how to extract necessary information from the spectra of a non-rigid rotor. Now, the spectra of the molecule HF has been studied very carefully and the data were noted. So, as I have discussed in the previous part that these green dot lines will indicate the position of the rotational lines given by a non-rigid rotor, and these lines were carefully experimented and noted for the molecule hydrogen fluoride. So, we have a large number of data, and you see this equation, that is nu bar spectra equals to 2b into j plus 1 minus 4d into j plus 1 whole cube. This equation was guiding the position of the spectral lines, as I have discussed in detail in the previous part. Now, we have the data, and after carefully examining the data, we can give a empirical fitting. We know the structure of this equation, and we have the data at which wave number the molecule HF is giving the spectral lines. So, from that data fitting is given carefully, and that was obtained to be 41.122 into j plus 1 minus 8.52 into 10 to the power minus 3 j plus 1 whole cube. So, this has been obtained semi theoretically. Now, if we compare this theoretical equation and this semi theoretical equation, we can easily say that the value of 2b is 41.122 and the value of 4d is 8.52 into 10 to the power minus 3. Comparing equation 1 and 2, we can at a glance say that 2b is equal to 41.122 and 4d equals to 8.52 into 10 to the power minus 3. So, what will be the value of b? Or b equals to 41.122 by 2. This is the formula of the rotational constant b. So, this expression gives us that b equals to h upon 8 pi square I c. Now, this I is mu r square. So, we get the value of b. From this we can have the value of I, and since I equal to mu r square, we will have the value of r, which is the bond length of this molecule. Now, I have shown you in the video titled bond length of carbon monoxide how to get the bond length from the value of rotational constant. Now, we have another similar problem. Watch that video, try to adopt that technique, practice it and apply that knowledge to this problem and find the value of the bond length of the molecule HF. So, this is your homework. Now, after obtaining this, please post it in the comment section of this video. I will check it whether you are correct or wrong. So, in this video I will concentrate on the another information, that is the fundamental vibrational frequency. So, a study of the rotational spectral lines for a non-rigid rotor will give us the bond length of that molecule, and in addition to that it will give another important information regarding the molecule, that is the fundamental frequency, that is the fundamental vibrational frequency of the bond within the molecule. So, this part I have given you the homework, please post it in the comment section, and I have already shown you the technique to find the value of bond length. Now, in this video I will concentrate on the fundamental vibrational frequency. Now, see, this is 4b cube by nu bar square equals to d. This expression has been derived by me in the previous part. So, from this we can write, we take this nu bar square to the right hand side and we take this d to the left hand side. So, it will imply nu bar square equals to 4b cube by d. See, nu bar square will be 4b cube by d. We have the values of b, we have the values of d. Now, the value of d will be 8.52 by 4 into 10 to the power minus 3. Therefore, nu bar square will be 4 into b cube. So, b is 41.122 divided by 2 cube by d, the value of d is 8.52 by 4 into 10 to the power minus 3. So, let us simplify it first before using calculator. So, it will be 4 into 41.122, it is cube, and we will get here 8 from this 2 cube, 8 here, 8.52 in the denominator, and it is 10 to the power minus 3 here. So, let us find the value using calculator. So, it is 41.122, its cube. So, into 16 divided by 8, so that will be 2 here. 4 into 4 equals to 16 divided by 8, so it will be 2 in the numerator. So, into 2 equals to divided by 8.52. So, it is 16323, it is 16323.49 into, now do not put this 10 to the power minus 3 in the calculator, we take this to the numerator. So, it will be 10 to the power 3 here. Now, this b will have the dimension centimeter inverse, and d also will carry the same dimension. So, when we put here, we will get centimeter inverse cube for b cube, and here it is d, so it is centimeter inverse. So, after cancellation it will be centimeter inverse square. Okay. Then what will be the value of nu bar? So, we have to square root it. So, we multiply it by 1000 and then take a root of it. So, it is 4040. See, for square root, the centimeter inverse square will be centimeter inverse. Now, the dimension of wave number is centimeter inverse, so it is okay, the calculation is correct. So, we have obtained the value of the fundamental vibrational frequency in terms of wave number. Now, this value has been obtained using rotational spectra. In the next chapter, we will find that where we will study the infrared spectroscopy, we will deal specially with the vibration of any bond. So, that is supposed to give more accurate data regarding the frequency of any bond. So, from that infrared spectroscopy study, the fundamental vibrational frequency that has been obtained for the molecule HF is found to be 4138 centimeter inverse. So, it is the accurate value. So, this value has been found for the molecule HF using the spectral data for the rotational spectra, and this value has been obtained accurately from the infrared spectroscopic data. So, this is more accurate since this is a direct measurement. Now, see what percentage of error has been crept in our study. For this percentage error, we will do this simple mathematics. So, accurate minus observed by accurate into 100. So, again we need calculator. So, 4138 minus 4040 equals to divided by 4138 equals to. So, it is 0.02368. 0.02368, that is equal to 2.36%. So, a negligible amount of error has crept in our study. It is only 2.36% error. Now, that error may have two origins. One reason is the error in measurement, that is obvious, and every measurement is associated with error. So, there must be uncertainty in measurement, and from that we have a contribution of error. Another contribution in the error may be due to the consideration of simple harmonic force field for the molecule. If you have watched part 1 of this lecture, then you can remember that we have considered the simple harmonic force field for the molecule we are studying, and actually the molecule is not simple harmonic. So, there from this consideration there may be some error that might have been crept in. However, this error is not that much. So, we can say that our result is in good agreement. Next, we know that the fundamental vibrational frequency in terms of wave number is related to the force constant of the molecule by this expression. So, what will be the value of K? For this, let us square in both sides. So, it will be 4 pi square c square, and here it will be K by mu, or K will be equals to 4 pi square nu bar square C square into mu. So, this is the expression of the force constant of the molecule. 4 pi square into nu bar square into C square into mu, that will be the expression of the force constant. Now, we intend to determine the value of the force constant, that is the another necessary information that can be obtained from the rotational spectra of a non-rigid rotor. So, now see, you have the accurate value and you also have the value that is obtained from the rotational spectra. Now, since our topic is non-rigid rotor, we will use that data that has been obtained from the rotational spectra. So, we will continue with this data and not with this, since this is obtained from the infrared spectroscopy that we will learn in the near future. So, we will start with this value. So, what will be the value of K? This is 4 pi square means 22 by 7 whole square, and nu bar square is there. So, 4040 square will be there. Now, for this we will get centimeter inverse squared. So, here I write centimeter inverse square. Now, we have C square, so it will be 3 into 10 to the power 10 and a square here. So, we will get centimeter per second squared, and then we have mu. So, let us determine the value of mu. So, we know mu is defined by m1 m2 by m1 plus m2. So, for the molecule HF it will be mH into mF by mH plus mF. Now, this is the mass of the single atom of hydrogen, this is the mass of the single atom of fluorine. So, the value will be 1 by Na gram into 19 by Na gram by 1 by Na gram plus 19 by Na gram. If you cannot follow this relation, then do a simple unitary method. Say mass of Na number of H atoms, Na number of H atoms is 1 gram. This is the atomic weight. 1 is the atomic weight of hydrogen. So, 1 gram is the gram atomic weight of hydrogen, and that will contain Avogadro number of atoms. So, what will be the mass of 1 H atom? It will be 1 by Na gram. So, this is mH. In a similar way, mass of Na number of fluorine atoms is 19 gram. It has 9 protons and 10 neutrons. So, it is 19 gram. So, mass of one fluorine atom will be 19 by Na gram. So, that is the mass of fluorine. So, we will replace mF by 19 by Na gram, and we will replace mH by 1 by Na gram. Now, students have a common mistake that they forget to place this Avogadro number, and they end up with bizarre results. So, if we simplify this, what we will get? We will get 19 by Na square here. We will get 19 into 1, 19, Na into Na, 19 by Na square, and it is gram square into, here we will have 19 plus 1, so it is 20, 20 by Na gram. So it will reverse, so it will be Na by 20 gram. Do you get it? We will have a LCM here, so it will be 19 plus 1 equal to 20 gram by Na. So it will inverse to give you 20 gram in the denominator and Na in the numerator. So it will cancel this gram square by gram, it will be gram in the numerator and 1 Na and 1 Na will cancel out. So it will be 19 by 20 Na gram. This is the value of mu. Now we have to put here this value. So we put here 19 by 20 and Avogadro number here, so it is 6.022 into 10 to the power 23 and gram here, so it will be, so let us take all these dimensions to the above line. So for this it will be centimeter inverse squared. See here it is centimeter inverse and we have square here, so it will be centimeter inverse squared. It is centimeter per second squared, so it will be centimeter square per second square and we have a gram here. Four into 22 square into 4040 square into here it is 9, it is 19 and in the denominator we will have 7 square, that is 49 into here it is 20 into 6.022. Now the powers are left, so it will be 10 to the power 20. Here it will be 10 to the power 20 and here it is 10 to the power 23. Check it. Now this centimeter inverse squared will nullify this centimeter square. So we will have gram per second square to be left over. Now we have to calculate this. Lot of things are there, so you have to remain calm while calculating this. So it will be 22 squared equal to into 4040 square equal to into 4 into 9 into 19 divided by 49 divided by 20 divided by 6.022. So the value is 915,582,254.5. Let us check. 915,582,254.5. Now from this we will have 10 to the power minus 3 and we have the dimension gram per second square. Now I am editing in this format. I am taking it as gram centimeter per second square into centimeter inverse. Now this centimeter and centimeter inverse will nullify and will remain the same as before. Now can you remember the definition of one dyne? One dyne is said to be the force which, when acts on a body of mass 1 gram, produces in it an acceleration of 1 centimeter per second square. So this 1 gram centimeter per second square, it is one dyne. And see this centimeter inverse. Now we know that 1 Newton equals to 10 to the power 5 dyne. So what will be the value of one dyne? One dyne will be 10 to the power minus 5 Newton. So we put here 10 to the power minus 5 Newton. Again we know 1 meter equals to 10 to the power 2 centimeter. We take this centimeter to the left hand side and meter to the right hand side. So it will be 1 centimeter inverse equals to 10 to the power 2 meter inverse. So we put here 10 to the power 2 meter inverse. So what it will give us? It will give us 10 to the minus 3 Newton meter. So what we are doing, we are actually converting this CGS unit to the SI unit. So this dyne per centimeter will be converted to dyne per centimeter is converted to Newton per meter. So it will give us 10 to the power minus 3 Newton per meter. Now these two will combine to give 10 to the power minus 6. Now we have the point here. It is 915,582,254, 0.5. So the decimal will come 6 digit before. So it is 1, 2, 3, 4, 5, 6. So it will be 915.582. This 10 to the minus 3 and 10 to the minus 3, it will be 10 to the minus 6. So when it is multiplied with this figure, this decimal will come 6 digit before. So it will give us 915 Newton per meter. So that is the value of the force constant. So from the rotational spectral data of a molecule, and here it is hydrogen fluoride, we have been able to extract two important information. One is the bond length of the molecule, that is given to you as homework. Please get the value using the technique I have shown you in the video, bond length of CO, and post it in the comment section of this video. And another important information we have been able to extract, that is the force constant of the molecule hydrogen fluoride. So the force constant is found to be 915 Newton per meter. So to expand the molecule by 1 meter or to compress the molecule by 1 meter, you need 915 Newton force. So that is a huge amount. So we can conclude that HF has a relatively strong bond. So this is all about the non-rigid rotor, and in the next lecture I will start the chapter infrared spectroscopy. So stay with me to have a sense of spectroscopy. Thank you.